Simulation and Modeling of Tri-Gate SOEN FinFET 10 nanometer, presented by Mr. Lazzaz Abdelaziz, supervisor by Professor Bosbah Khaled, Professor Gamia Mustafa, Attachment Laboratory, Laboratoire des sciences de la matière condensée, LSMC, Université d'Oran 1, Ahmed Ben Bella. Summary. Number 1, introduction. Number 2, presentation of the Tri-Gate and FinFET 10 nanometer SOE. Number 3, theory of the Tri-Gate FinFET 10 nanometer SOE. Number 4, geometrical and operating parameter. Number 5, results. And number 6, conclusion. Introduction. In recent years, the transistors have undergone the green miniaturization, which has allowed them to be integrated and manufactured in the same shape. But the scaling of the transistor is approaching the quantum limit, where the classical model are no longer valid. At this quantum scale, many phenomena appear which alter the functionality of the device, namely the leakage current and the increase in threshold voltage, the variation of dopants concentration in the channel, Dibble-Giddle, and the ion per I-off ratio. The work presented in this paper is about the modeling and simulation of Tri-Gate SOEN FinFET 10 nanometer using the NEGF, non-equilibrium green fiction method. We use the geometrical parameter of the Berkeley Spice model PTM 10 nanometer, and we calculated the functional parameter of the device. Now, presentation of Tri-Gate and FinFET 10 nanometer SOE. The left figure present the structure of the device, such HSE is the height of fin, WSE is width of the fin, and L is a channel length. With the blue color is the oxide used in these simulations. The drain and source and substrate are with yellow color and with the silicon semiconductor. In the right figure represent the vertical presentation and structure of our device. Theory of Tri-Gate and FinFET 10 nanometer SOE using the NEGF non-equilibrium green fiction method, which describes the ballistic and the quantum transport in the nanoscale channel. The drain current in 3D is represented by the following equation. L is the channel length, K is the constant Boltzmann, T is the temperature, Q is the electron charge, mu is the mobility, QA is the charge in channel, CF is the correction factor, and VD is the drain source voltage. The drain current in the short channel is modified by correction factor. W is fin width, L is the channel length, and TSA is the thickness fin. The transconductance is represented by the following equation. So, the transconductance equal the variation of the drain current per the gate voltage. The threshold voltage in this structure is calculated by the following equation. VTH is the threshold voltage, Phi-ms metal semiconductor work function, Phi-f Fermi potential, Cox the gate capacitance, QD the depletion charge in the channel, QSS the charge in the gate dielectrical, Vin the input voltage. The subthreshold slope in the device can be calculated by the following equation. SS equal the variation of the gate voltage per logarithm of 10 the drain current. The leakage current is directly related to the SS, and it can be given from the following formula. So W is the width fin and L is the channel length. The drain induced barrier loading Dibble effect is represented by the following equation. Dibble is the millivolt per volt equal the variation of the threshold voltage per the drain source voltage. Now we present the geometrical and operating parameters. First, L is the channel length 10 nanometer. W is the width transistor 50 nanometer. W fin is the width of the fin 7 nanometer. The threshold voltage 0.4 voltage. The oxide thickness 1 nanometer. Height gate in this simulation, the oxide used is the hafnium 24. Mu the mobility 650 centimeter square per volt multiplied second. The supply voltage 0.8 voltage. Now we present the calculated parameter. The initial current is 10 microampere, gamma 0.37, OT equivalent oxide thickness 6.15 nanometer. Result. The first figure represents the transconductance characteristic tri-gate SOE and FinFET 10 nanometers. The transconductance vs the gateway voltage. We notice that the transconductance starts to increase for the gateway voltage equal the threshold voltage, for the drain source equal 0.7 volt. In second way simulations, we present the transfer characterization for tri-gate SOE and FinFET 10 nanometer. So the drain current vs the gateway voltage with VDS equals 0.25 voltage. We notice that the drain current starts to increase with voltage gate equal the threshold voltage. Finally, the output characteristic for the tri-gate SOE and FinFET 10 nanometers is represented. Drain current vs the drain source for the gate source equals 0.5. We notice that the drain current starts to increase for the drain source equal 0.1 point voltage. To study the performance value of the device, we need to calculate different parameters such as dipole, on current, off current, and the ratio on current, off current. The performance value rate is represented in the following table. First, SS. 81.61 millivolt per decade. Dipole 9.16 millivolt per volt. On current the 23.09 milliampere. Off current 1.66 picoampere and ratio I on per I of 13.9 billion. The International Technology Roadmap for the Semiconductor recommendation for the ratio I on per I off is more 1 million. So in our device simulations, the ratio is more this value. Conclusion. The FinFET 10 nanometer tri-gate SOE semiconductor on insulator is a device that has marked its reliability given the good performance result obtained with the different simulation and the use of the hafnium oxide. To have an application on the different circuit where the optimization with the good choice of the parameter is expected. The several perspectives are expected for this type of the device, such as carrier mobility in the channel and the threshold voltage control, phonon interaction and oxide faults. Thank you.